Welcome to the second part of the micromechanical processes. We've started looking at some of the etching approaches to create 3D structures in silicon. If you want to look at anisotropic etching and the wet etching processes first, what comes to mind is potassium hydroxide, TMAH, tetramethylammonium hydroxide, EDP, and a few others. KOH constitutes today sort of the standard process. It's a comparably cheap and simple process. The main thing you have to do is control the concentration of your KOH and the temperature. Make sure that in your etching solution you have a constant exchange through a magnetic stirrer and clever placement of samples, as well as proper temperature control of your solution, that you end up with a well-controlled environment, because of course the etching depends strongly on your concentration and the temperature. Now, how does this reaction actually work? Well, it's the reaction mechanism is such that you're starting off first by having the silicon react with these OH groups that create essentially a complex that then reacts with further electrons that provide further OH to really create this component here. And this one can actually be dissolved, is soluble, and then turns this into a component that is solved in your solution, and hydrogen that escapes. So again, how this works: you take your OH, you create this complex here, you have additional electrons. These additional electrons help you create more of the OH groups. That is important, because this is a way we can interrupt this process. If we take these electrons away, the process will slow down and stop itself, which is something we can do by using electrochemical etching reaction, where we sort of apply specific voltage, current, etc. We can use different levels of doping in our semiconductor to then essentially remove the electrons that can then not contribute to further creating the OH groups that are necessary. So by creating those, we can then couple this complex with more OH groups, creating this one and more water. And so the overall reaction looks like that. You get the solvable complex, and then the bubbles that you see rising from the surface are actually hydrogen. This picture you've seen before. So this would create a structure, KOH, TMAH, tetramethylammonium hydroxide, and others can help you create these structures because they have different etch rates and different crystal orientations. The characterization, again, as I mentioned, is usually done by looking at different concentration ranges for your KOH and the temperature. And as you'll find, obviously temperature has a significant impact, and your concentration. That is why typically you'll find a sweet spot somewhere in the 20 to 30% range. That's where a lot of the etching work is being done. And the etch rates that you're observing are around about a micrometer a minute, sometimes a micrometer and a half a minute, which means that if you're etching through a typical wafer, 390 micrometers, maybe need a 30 micrometer diaphragm you'd like to create, you have 360 micrometers to etch through. That gives you 6 hours of etch time that you need to look at. As I mentioned, temperatures you've seen, of course, is very important, the concentration as well. How do we maintain these? Well, if you wanted to have a fairly simple setup, you go for a dual-walled etch vessel. So unlike just a standard glass beaker that you use with a hot plate or a stirrer, you'll take a dual-walled one through which you're running a thermal oil that maintains the temperature at a constant temperature throughout the solution. You probably add a magnetic stirrer to add forced convection. And then you want to put on top a lid with a reflow cooler. Why? Well, obviously, as you start heating up the solution, part of the constituents are going to start evaporating. Much of the water will escape, which means that the concentration for your KOH will change over time. A way to keep that constant is essentially put a lid on top and a reflow cooler, so whatever evaporates condenses again, drips back into the solution, and then means that you maintain the concentration of your KOH. If you look at the edge fronts, it's a good idea to start understanding where the different crystal planes are. Obviously, as you have a 100 wafer and you look at the 111 planes, those are at a 54.7 degree angle. You can just compute that by looking at the cosine of the angle as being the product of the two vectors normal to those planes divided by the product of the absolute value of those vectors. So that's fairly straightforward. In a 110 wafer, you will find that the slower etching 111 planes are at a 90 degree angle, depending on some orientation. In the other case, they're about 35 degrees. And so you can create fairly accurate square channels as well. The precision that you accomplish, given that is governed by the selectivity between the different crystal orientations, and typically if you've got a well-run etch process between the 100 fast etching plane and the 111 plane that etches slower, you may have an aspect ratio or an etch rate ratio of 1 to 51 to 100. Now, that also allows you to create structures in the crystal that, for example, allow you to create something like what you see in this picture here, a very precise V-groove, because if you open a rectangular window, you start etching. Of course, this starts off as a pyramid type shape, but eventually you're going to get to a point where those 111 planes meet, and then the etch process pretty much stops. And that shape is very well defined. This is a structure that over the last 15-20 years has increasingly been used, for example, in aligning glass or optical fibers into wavegate structures in a wafer. So this allows you to, in a precision way, align the optical fiber with an optoelectronic device or a wavegate structure that you'd like to align it with without having to worry too much about the external packaging solution. So very, very clever and cost-efficient approach. This one we already talked about. You've seen this one in the 110 wafer, just here as a proper illustration. Now, when you start etching the silicon, of course, you need to start thinking about your etch mask and some of the other materials that will also be exposed to your KOH. And typically these will be silicon oxide and silicon nitride as the most commonly used materials in MEMS and semiconductor structures. Silicon oxide is a dielectric, the nitride is a dielectric and passivation layer for active surfaces. The silicon nitride, as we'll see, is hardly being attacked at all. The silicon oxide is being etched by the KOH, albeit at a much, much smaller rate. What you can see here is that we're looking at something that is closer to 60 nanometers an hour than 60 micrometers an hour, but it's also concentration dependent. So it is something that you need to take into account. If you have structures that are not very deep and you're willing to sacrifice some of the oxide, an oxide mask may be okay. Most cases you will likely want to have a nitride mask. This picture is important insofar as it's the basis for any kind of geometry that you're trying to define. So something that you need to understand is as you start doing anisotropic etching, and this one again assumes a 100 wafer in KOH, is essentially it's a trigonometry exercise and a bit of an undercut exercise. So let me look at this in a little bit more detail. Typically what we may want to accomplish, and I'm going to turn this around now, is the structure that I've drawn many times before, something that may look like that. This is our silicon. Now what we're really interested in is typically this part here, because this is part of either a pressure sensor or an accelerometer or any other structure. And really what we need is something that has a defined thickness D and a width W. How do we get there? Well, since we start etching that from down here, we need to be able to determine how to get here. Obviously, if we know that this is 54.7 degrees, we can now determine where this point is, where the etching is supposed to start. Now we need to take into account, obviously, the aspect ratio and the etching rate. So if we went for this example where we use 390 micrometers thick of silicon, let's see D is 30 micrometers. That means that this one here is 360 micrometers. Now let's assume an etch rate of the 100 to the etch rate of your 111 direction as being 100 to 1. What that means is that if I etch 360 micrometers this way, I'll be etching about 3.6 micrometers this way. And so again, I have to project that in there. That leads to some level of undercut, and it means that I need to compensate for it in the mask layer that I'm using here. So that is important to understand, that when I then design the mask for my lithographic process and how wide open that window is that I'm using to etch this cavity, that I take into account the trigonometry, and that I take into account the undercut, so that I end up with a structure that then in the end gives me whatever the determined width W is for the structure that I'd like to accomplish. That's important. So in some cases, as an additional word of caution, if you were to have a double layer, for example, you have your silicon oxide and your silicon nitride. For this etch process, which may last 6 hours, you definitely want to have a nitride film that is your actual mask. Why do you not put that directly on the silicon? Well, let me draw another picture very briefly. Well, I'll try to do this on this picture. How do you pattern your silicon nitride? You'll probably use a dry etch process. This dry etch process has an etch rate somewhere in the, maybe 20 nanometers a minute in your nitride. If that process hits the silicon, that will jump to close to a micrometer. So let's assume for a moment here, and I'll take this one out, that we just have a nitride mask. Let me just draw that for a second. Here is our silicon surface. This is just the nitride mask. Now we need to remove that. So we open it with a dry etch. So let's say it starts hitting the silicon in some areas. There's no etch stop there. Well, that's already a bad design, because that now means that as I hit this interface, my etch process doesn't slow down so that I can control how much I've etched. It actually accelerates. Now you may say, well, I'm going to etch the silicon anyways. I don't care. So maybe I end up with something that goes 5 micrometers. Let's say this goes 5 micrometers into the silicon. I'm going to etch that anyways. Important. Where's my 111 plane now? The one where the etching is slow. That does not start at this point anymore, but my 111 plane is now suddenly here at this point, because this is the first time that you have exposure to the 111 plane. So instead of getting something that stops here, you're now getting something that stops here. So your entire geometry is messed up. How do we fix that? Well, by making sure that we have a well-defined surface where our etching starts. How do we do that? Well, we need to make sure that we don't just run through the nitride and into the silicon. So we need an etch stop. Fortunately, in many of the processes, so one of the ways of doing that is having an oxide film underneath that fortunately exists. In most of those cases, automatically you start with a silicon wafer. First you put your oxide down as a dielectric or a field oxide or a mask for your ion implantation. Happens on both sides, it's a thermal oxide. Then in most other cases you also immediately follow up with a silicon nitride film as a passivation layer. Again, most of the time it's an LPCVD nitride, high temperature process. It's on both sides of the wafer. And so we already have what we need for our etch mask on the back side of the wafer. That's very elegant. And the dry etch process for our silicon nitride stops on the silicon or slows down considerably on the silicon. So now we have a situation where, we do our lithography on the back, we etch our silicon nitride, we stop on the silicon oxide or we slow down. Now, of course, we still need to get rid of the silicon oxide. Well, we can use a buffered oxide edge or an HF edge, which does not attack your silicon nitride. It does not attack the silicon above it. It just removes the little bit of oxide, whatever 200 nanometers that you may, or 100 nanometers that you may have in there, that work perfectly well as an edge stop for the dry edge of your nitride. We remove that in a quick BOE or HF dip. You're done. And then you have the perfect silicon surface exposed and you can start your KOH. So this one is really important, and again, the way we usually build devices even helps us in having that structure in place to start with. Some of the important parameters that we want to look at is, of course, the impact of doping concentration. So something that we see, for example, is that we get a significant drop in etch rate at high boron doping concentrations. And the way to explain that is, and you can see that in this curve here, I explained that before, is that you're really finding a way of removing or blocking part of the reaction process. You can see that happens at fairly high concentrations where the semiconductor becomes almost conductive. We'll look at some of the details in the next section, but in short, what you're making use of is think of the different steps that we have in our KOH etch process. There was a place where electrons are being generated that again help create further OH groups that are necessary to complete the complex that is then solvable in your solution. What do you think happens if suddenly we go towards a substrate that has comparably high conductivity? Those electrons go away. Thank you very much. I'll see you for the next class.